This video is going to focus on doubling time, which is a special case of within exponential functions. Doubling time is the amount of time it takes a quantity to double its initial amount. And when you're thinking about that, the reality of what happens is double an amount is a multiplicative relationship. So we're still looking at a relative rate of change. And it's not necessarily over a single unit of time. But we can take that doubling time and sort of convert it back into what is more our traditional exponential function form. But then there's also some sort of shortcuts and tips that might make your life a little easier if you're inclined to use them. So what you see in the box are a bunch of the shortcuts and tips. I'm going to be using them, but I'm also going to be referring back to some of the exponential function stuff we've been dealing with all along. So let's take a look at this doubling time problem. We're told in July 1953, the U.S. population was 160.2 million, and by July 2011, the population had doubled. So I'm going to start by making a little table of values for myself. I'm going to call 1953 year zero. And in year zero, we had a population of 160.2 million. And in 2011, that would be 58 years later. We now had a population that was double the amount. So that would be times 2. So 320.4. And from here, I can build an exponential function that would help me answer the question here. It's saying, what is today's population if this trend continued? Well, to start with that, I'd want to find my sort of growth factor. And I can do that by taking my new value, which would be 320.4, and dividing it by my original value, the 160.2. And to turn that into an annual rate, I'd raise that to the 1/58th power. Now, before I go too far here, let's do a little bit of simplifying here. If you notice in the parentheses here, the 320.4 over 160.2 actually simplifies down just to 2. And then I'll keep that 158. But the 2 here is what I wanted to draw your attention to, because if you go back up to this box here, you'll notice that a bunch of these, instead of that 1 plus r, we now see our parentheses are filled with just the 2. Because we're looking at a growth factor of 2, we're sort of multiplying by 2 to make that change. But it's not over a single unit of time. Instead here, we got that, 58 years that went by. And we only wanted, to figure out our annual rate, we only wanted one of those 52, which is why you sort of, you see the sort of 2 parts here. You see the time it takes to double in the denominator of your fraction and the time that you're looking for. So this value right here, that would get us sort of our annual, factor, growth factor, if I wanted to multiply it out. Now in this case, I don't actually want the annual factor. I want the population if this trend continued to, 2023. So I'm looking, 70 years later. So I'm going to actually set this up, but instead of 1/58, I'm going to set it up 70/58 because I want 70 years worth. And so that sort of becomes my sort of like growth factor. And then I'm going to times it by my initial amount. And so I'm sort of using this piece of the equation. And the initial amount was that 160.2. And I would end up with a sort of total population in 2023 of 369.8 million people. Hopefully from that you can sort of see some of the trends from our earlier problems. We just sort of now have some special cases to make our life a little easier. Using that sort of setup we have right up here, we can then do this next problem. So we're going to take this sort of building block and use it down here. So we want to estimate when the population will be 400 million people. So we're looking when the output is going to equal 400. We still have that same initial value. and then we're going to have 2, but this time we're not going to have that 70 because that's what we don't know. So we want to figure out what that time needs to be in order to get 400 million people. And so you sort of notice the structure I have here. This is the piece I want to know. And this is built to what we did before. Remember I said how the 2 to the 1 over 58 would get me my annual growth rate. So it is within this, sort of simplified within some exponent rules. Now I'm going to skip this for now, but if you remember in the previous videos, at this point I could use some guessing and checking or graphing. I already did that, and if you did that out, you would get t is equaling around 76.5 years later, which would be either somewhere between 2029 and 2030. You know, probably halfway between. Since this was July, maybe January 2030, December 2029, you know, one of those months in there. Now, I've sort of hinted at it, but from here we could build an actual exponential function, which might have been easier to do within part B. I sort of wanted to show it with the growth, the doubling factor function. But if I actually wanted to build its own function, I'm going to go back to sort of what I started with up here. And we're going to actually calculate out that annual growth rate. So we had 2 to the 1 over 58. And if you multiplied that out, you would come up with your annual growth rate of 1.012, 022. From here, I can write my sort of exponential function. So I still have that initial value of 160.2. I'm now going to replace my base of 2 with this new growth rate. And I'm going to raise that all to the t power, with t still being years since 1953. A note, and I think I just used the wrong term in there. That's not a growth rate, that's a growth factor. I was asked here to find the rate. Remember, the rate is when we take, we're going to minus 1 there. We're looking for the percent. So the growth rate would be the percent form of this number, which would be about 1.2%. Would be the annual growth rate according to this model. Now, that's actually much bigger than the actual population growth rate. Today's natural increase is more like 0.12%. And we can approximate how many years it will take the population to double. Now, I could build an exponential function and sort of solve it out. But there's a sort of simpler way when it comes to doubling that we use, and it's known as the rule of 70. And of all the doubling time shortcuts, this is one that's sort of nice to have that gives you a quick sort of estimate. And when we're talking about every day, like, it's nice to have an estimate. If someone's like, approximately when do you think something will double if it has this annual growth rate, if I'm thinking about investments or other things like that. And here's the rule. I take 70 and divide it by the percent in its percent form, and that's going to tell me my doubling time. And this rolls up in the box. I just didn't feel like flipping my screen back up. And so I'm going to do here 70 over 0.12%, and I would get out 583.3 years. So at the rate of 0.12%, which is a very, very small growth rate, it's going to take an awful long time for our population to double. To give you a sense, changing it even to 1.2% would only take us 58 years to double. So significant difference. That's a super small percent. We're going to sort of keep with this, looking at rates and figuring out annual growth rates on this next problem. Just doing a sort of a two comparisons. A little bit of COVID-19 data. So from April 4th, 2020 to April 10th. And so this right here, and I'm going to change colors just to sort of flip things up a little. This is a 6-day period. So over this 6-day period, the number of deaths doubled. They also doubled again from the 10th to the 21st. So that's the 11-day period. And so which period did the number of deaths increase the most rapidly? And so in both of these cases, we're looking at doubling. And we know they doubled, this here doubled every 6 days. But if I can figure out the daily growth rate, that would be 1/6. And that would come out to 1.1225. And so there's my growth factor. If I take 1 away from that, so 1.1225 minus 1, take out the 100%, that would tell me that the number of deaths was increasing by about 12% each day. That's pretty high. Versus over the 11-day period, that would be 2 to the 1/11th power. And I get a growth factor of 1.065, which is about a 6.5% increase every day. I should be writing out increase on these. And so which time period increased faster? That April 10th to April 4th to April 10th period was a significantly higher increase than April 10th to 21st. And that makes sense. It doubled in a shorter period of time. And so it makes sense that that increase would be greater. So part of the goal I wanted you to come away with this video is realizing that doubling time is just another form, a special case within our exponential functions. It's not a whole new set of rules you need to memorize. There are some nice to know shortcuts, but they're not necessary. Stay tuned for the next video in which we take a closer look at half-lives, another special case.